You're motivated by the search for life.
That's right.
Life on Earth everywhere has uses liquid water. Typically when people think about an ocean world other than Earth, they go straight to Europa. You're going to Europa, low dipping over Europa, but you're not landing there.
Now, normally when we think about a spacecraft flying by a world, it's thousands of kilometers away. We'll orbit Jupiter, but make these flybys of Europa, and the close approaches.
How close are you gonna get?
25 kilometers.
What?
Are some of the closest ones. And
that's as close as any object has ever swung by anything. Suppose you could just tell Galileo what you're about to do. What a privilege that would be.
Oh, absolutely.
This is StarTalk. Neil deGrasse Tyson, your personal astrophysicist. Today we're going to talk about ocean worlds. Ooh. And we got with us a previous guest on StarTalk, Kevin Hand. Kevin, welcome back.
Hey, my pleasure, and welcome to JPL.
Oh yeah, this is not my office, is it?
You made a great trip out here.
It's not my office.
Yeah.
In your turf at Pasadena, California, the Jet Propulsion Labs. I don't ever presume that everyone knows what those three letters stand for, but you can take it for granted if you work here.
Right.
Everybody knows. I don't think everybody knows. Jet Propulsion Labs and water worlds is your thing.
It is.
And my God, just at the dawn of COVID, you had a book by that title.
That's right. Alien Oceans.
Alien Oceans.
Yep.
There it is.
Yep.
Typically when people think about an ocean world other than Earth, they go straight to Europa. At the top of everybody's list.
Yeah.
I don't know if it has a better PR agent or what. And so, but if you abstract that idea and go to any place that might have sort of liquid in the world doing anything, that list goes up.
It does, absolutely. And these ocean worlds, Europa is sort of the mother of ocean worlds.
Yes. Europa, again, a moon of Jupiter.
Correct.
Yeah.
And even back in the late 70s, we could see with the Voyager data that something curious was going on with Europa. And over the course of the past several decades, we've now come to learn and appreciate that the outer solar system has got a small fleet of ice-covered worlds, and beneath their icy shells, these moons of the outer solar system have liquid water oceans. And of course, the big picture for me is the search for life beyond Earth.
That's your guiding star.
Guiding star. I would love, life on Mars, exoplanets, SETI, et cetera. But these ocean worlds like Europa and Enceladus and Titan, these are worlds where life could be alive today, extant life.
Oh, because when you're looking at Mars, no one really thinks anything's going to be crawling around on its surface.
Exactly.
Whatever might have been happening billions of years ago, because there's no active water activity on Mars.
Well,
at least not on the surface.
Exactly, not on the surface. There could be on the subsurface. Who knows? Maybe there's life in the subsurface on Mars. But our search for life on Mars is a search for past life. And the molecules of life don't last long. So like DNA, RNA, proteins, the stuff that makes our biochemistry.
But bones last pretty long.
Well, bones do last long, and it's not inconceivable.
Don't tell Lucy that we didn't find life.
Yeah.
Lucy would beg to differ.
And as you appreciate, back in the Viking days, even Carl Sagan wanted to leave, put some lights on the Viking lander. So what if there's a Martian mouse, right? So a Martian mouse would leave bones behind.
Yeah.
Bones do last for a long time, but for the most part, we're talking about the search for microbial life, and microbes do actually leave behind minerals.
By the way, if a microbe had bones, I don't want to meet it. I don't know what the hell that microbe is doing.
Well, some of the most beautiful, if you ever see travertine or some of the beautiful rock structures that are used.
Or the Burgess Shale.
Yeah.
I think, is that in Canada, I think?
Yeah, Burgess Shale has got animals, but
okay.
There are...
Because that was after the Cambrian explosion, if I remember correctly, or during it.
In that time frame.
In that time. So they took on very interesting shapes, but they got preserved.
Yep.
That's my point of that, right?
Yeah, exactly. Whereas microbes can mediate rock structures. And if we see sort of a weird wavy rock form, sometimes referred to as a microbial or a stromatolite, that is a form of an inorganic biosignature for microbes, kind of like bones for microbes in some ways.
I like
it's
that
more of
analogy.
it's more of a frozen apartment building for microbes.
And you knew somebody lived there because it's an apartment building.
It's an apartment building,
yeah.
but you want to couple that observation of the strange rock structure with some detection of organic compounds or other things. But that's all for Mars, right? Looking at life in the past, billions of years ago on Mars. When it comes to a separate independent origin of life and a separate tree of life, we're going to be kind of constrained on Mars because those large biomolecules of, if life on Mars utilized DNA only lasts like maybe 10 million or at best tens of millions of years in the rock record. So we're not going to get like Martian DNA from samples returned from Mars. On a world like Europa, on a world like Enceladus, these are worlds where if we find indications of life on the surface of the icy shells, that's most likely, I would argue, an indication that life is currently alive in the oceans below. And that's extraordinary because then we can actually study it and see, does it run on DNA, RNA, and proteins, or is there a different ballgame
Mechanism altogether.
Yeah, contingent
that would
versus
completely
convergent.
transform everything we know of biology.
Exactly. Contingent evolution versus convergent in terms of
What is contingent evolution?
the impact that caused the dinosaurs to go extinct is perhaps a somewhat useful, though mildly flawed, contingent example. You could say that humans would not be here if it weren't for the impact that wiped out the dinosaurs.
That is definitely the case.
Well, but you might argue that at some point something else would have wiped out the dinosaurs. But you get my point.
No,
it's
it's
contingent.
definitely the case.
Yeah.
Okay, I work at a natural history museum. We got bones everywhere.
Yeah.
Okay. I'm telling you, here's the argument for that. Just hear me out if you didn't otherwise know this.
Yeah.
Do you know when T-Rex went extinct 65 million years ago, do you realize more time had elapsed between the extinction of the Stegosaurus and T-Rex than the extinction of T-Rex and today?
Yeah.
So dinosaurs thrived for hundreds of millions of years.
Yeah.
If you say, well, something might have still taken them out in the last 65 million years, I don't think so. Because it would have taken out a whole lot of other things and we would have known about it. Dinosaurs were a highly successful phenotype. Phenotype, is that the right word? No. Highly successful branch in the tree of life, the collective things we call dinosaurs. So I think they would have been here and we'd still be scurrying underfoot, not trying to get eaten as a snack by whatever the version of T-Rex is that survived today.
Exactly. So I'll remove any nuance, and say that is contingent.
Okay.
And then convergent is something like eyes.
I got convergence. Yeah, that one where a highly useful feature evolves completely independently, and to serve the same purpose.
Exactly. So something that I find fascinating is when it comes to the origin of life, is the polymerization of amino acids or nucleobases, et cetera, is that something that we're going to find is convergent? So life on Europa or Enceladus evolved to use DNA also.
Is it inevitable?
Right. Yeah. Or is there some other way to get that biochemistry done?
Now, the best argument I've heard for DNA, although it took me part of the way there, but I'm still skeptical because of the complexity of a DNA molecule.
Yeah, it's crazy.
A geologist said, look, when we go to other planets, the geology is familiar, right? A rock crystal of these atoms crystallizes the same way if given the right temperatures and pressures here as in there.
Right.
And so if the geology repeats itself, no matter what planet we're on, maybe biology will repeat itself.
Exactly.
And I thought, okay, I threw a bone to that, and I said, all right, let me hang with that for a bit. But speaking of bones, I got a bone to pick with you. You lumped Titan in with Enceladus and
Europa.
Yeah. How dare you?
Go on.
You're motivated by the search for life.
That's right.
Life on Earth everywhere has uses liquid water.
Yep.
There's no liquid water on Titan.
Well, to be clear, there is. We do think that beneath the ice shell of Titan. There is an ocean trapped beneath that thick ice shell. But I think you're referring to the fact that on the surface, we got these liquid methane and ethane.
If you have liquid methane, you don't have liquid water.
That's right.
Just to be clear about that. Okay.
Exactly.
But it's not just a given that every moon is going to have a heated interior from tidal forces. Now, I didn't do my homework on Titan before this interview, but is it subject to the same tidal stressing of its physical body as Europa and as Enceladus?
It's a bit of a more complicated story, specifically at Saturn. And this is, the story is complicated.
Titan, moon of Saturn. Yes.
Right. So Titan and Enceladus and the moons of Saturn, when it comes to the tides and how much tidal energy they have now and have had in the past, it's a bit complicated because the various moons go through resonances, right? Kids on a swing set kind of pumping each other up to swing in harmony or out of phase, right? In the Jovian system with
Jupiter system.
The Jupiter system with Io, Europa, and Ganymede, those three moons are right now in a beautiful resonance we call the Laplace resonance. So for every 2 times Io goes around Europa, Io goes around Jupiter, Europa goes around Jupiter once. For every 2 times Europa goes around Jupiter, Ganymede goes around Jupiter once.
I did not know they were in resonance.
Yeah, and so that's what keeps their orbits slightly...
So the system evolves to that because the dynamical forces favor it.
Exactly. So gradually the orbits widen out, and then Io starts tugging on Europa, and Europa on Ganymede. Perhaps someday Callisto will be part of the party, but right now it's not.
So that would complete the big four: Io,
Europa, Ganymede, and Callisto.
Yeah. The 4 that Galileo discovered.
That's right.
Yeah, we got to call them Galilean moons.
Yeah.
In fact, he called them stars, I think.
That's right.
The Medicean stars.
He was no idiot. He knew where the paycheck was coming from.
Because they were just points of light that moved around Jupiter. And why think it's a moon if it's just a dot of light? It looked like a star.
So he started off really well with like naming the stars, the stars of Medici. The Medici family was all happy. And he was like, oh no, these things go around Jupiter. Next thing you know, he's under house arrest.
Hey, StarTalk fans. I don't know if you know this, but the audio version of the podcast actually posts a week in advance of the video version. And you can get that in Spotify and Apple Podcasts and most other podcast outlets that are out there. Multiple ways to ingest all that is cosmic on StarTalk. What then? Why not call Io an ocean world?
Well, let's zoom out and think about kind of a Goldilocks scenario, right? In the early days of astronomy and planetary science, our conceptualization for habitability was kind of framed around this Goldilocks scenario: Venus, Earth, and Mars. Venus is too hot, Mars is too cold, Earth is just right, and that's all mediated by the energy that the planets receive from the sun, from their central star.
Not just that, the energy that reaches the surface, because you can reflect away some energy and that doesn't participate in the energy equation. Yeah.
And so the thinking back then, and still today, is that in order to have an Earth-like habitable planet, you have to be at that right star planet distance so as to maintain and sustain liquid water on the surface of your world. Whereas what these ocean worlds of the outer solar system are teaching us is that there's a new Goldilocks in town. It's a Goldilocks where the energy for maintaining and sustaining liquid water comes not through your parent star, but rather through the tug and pull and mechanical deformation and friction and internal heating of tides, of getting stretched by Jupiter, which is some 318 times as massive as the Earth. And so back to your question about Io, in this analogy with a new Goldilocks, Io is kind of like Venus. Billions of years ago, Io may have had water, but Io is the most volcanically active body in the solar system, and it has since lost any water that it perhaps had in the early days.
Oh, you misunderstood my point.
Go on.
You misunderstood. No, I didn't make myself clear. Your book is titled Alien Oceans.
Yeah.
You're talking about ocean worlds. You didn't specify water ocean.
So you want to qualify a magma?
Magma ocean on Io.
Well, I told you at the beginning.
If it's the most volcanically active object known,
you find life forms in a magma ocean. That's
I don't know. But
fair enough.
I guess, but you're right. If it's hot enough to melt rock, probably there's no life hanging out doing a backstroke.
Yeah, but you are correct in that there have been some nice papers on a magma ocean in Io because that tidal energy dissipation is so extreme.
Yeah, okay.
So from a habitability standpoint, it's got a game over.
Okay, but also I wanted to think very freely because you guys make me do this. If we go to Titan, where it has enough atmospheric pressure to sustain a liquid state of methane, because without pressure, then you lose your liquid, the range of temperatures where you can keep a liquid, right?
Right.
So maybe life does not require liquid water. Maybe it just requires a liquid. Can you imagine a life form where it is liquid methane coursing through its veins or whatever circulatory system it has?
Yeah. So I really hope that kind of weird life exists on Titan. The challenge is I actually have a bit of a hard time formulating an hypothesis that it could exist. So, for example, Europa and Enceladus, we can say...
Why should nature care what you have a hard time figuring out? Are you the metric of what exists in the universe?
You're 100%
I know you wrote a book on it and everything. I get that, but still.
Right. But when we do experiments, obviously with a scientific method, you formulate an hypothesis.
Yes.
And so I can formulate a hypothesis that life on Earth is based on liquid water, a suite of elements, and some energy to power life. I can then look at worlds like Mars and Europa and Enceladus and say, check, check, check. Now there's a fourth element there of time and stability that we can come back to, and there's some differentiation. But Mars, Europa, and Enceladus, I think we can check the box on liquid water and the other keystones for life. With the liquid methane on Titan, it's hard for me to say, based on what I know of life on Earth, or even oil fields on Earth, that a hydrocarbon liquid could give rise to life. And here's the sort of key chemical difference. Liquid water is a polar solvent, right? So in liquid water, we can dissolve other polar compounds.
That's the shape of the molecule, right?
That's right. It gives a little plus minus.
It's got hydrogen and oxygen and two hydrogens coming off at an angle there.
Yep.
Yeah.
Yeah, and so we get the electrons get sort of preferentially positioned such that you end up with a plus and a minus with the water.
So just correct my chemistry if I get it right. So if the two oxygens were sticking straight out on either side, then the molecule itself would have no polarity. In that sense, correct? And that is, there would be no difference between one orientation and another, and water would lose all of its really cool properties that we cherish.
Well, the positive and negative actually comes a little more from the hydrogen and oxygen differentiation, right?
Well, so it's not the angle that they're coming down?
The angle plays a little bit, but the...
Okay, that's just my... Thanks for filling in my chemistry.
Yeah, if you split it down the middle, like the oxygen is on one side of the V and the hydrogen is on the other. Yeah, and so if you flattened it out, you would definitely affect the charge distribution.
Yeah, that's what I thought. Yeah. And it would just be, it wouldn't be as effective at things we care about. Yeah. Yeah,
and certainly, coming when it comes to ice, you wouldn't get that beautiful hexagon that is in part due to the V shape of water. I think it's like 109 degrees and then 107 depending on liquid and solid form. But liquid water, great at dissolving other polar compounds. Liquid
universal solvent, we call
universal solvent for life on Earth, right? But you go to Titan, and now you've got these cold by our standards, liquid methane lakes and seas, and liquid methane is non-polar, and so you're talking about life arising and thriving in a non-polar solvent. And that just makes me scratch my head. It's like, could that work? I sure hope it does. I sure hope Mother Nature is
I'm just saying, if you go back 100 and whatever years, and when evolution was first a thing that people discussed, and in fact, Darwin himself might have called for this, is what we need is a 72-degree tide pool. So it's just right for life to form. And then the more we looked, it was like, no, you don't need that. You can do it this way.
Yeah.
In fact, you don't even need sunlight. I'm old enough. I'm an old man here. My textbook said life requires sunlight. All right, that's before we had the undersea vents,
Hydrothermal vents,
which got geochemical energy, thermal energy down there. So, and now even in modern astrophysics, planetary astronomy, the Goldilocks zone is insufficient to get it all the places where you'd have liquid water. So this is an exercise in broadening any definition we previously laid down for what we'd expect of life.
Yeah. And I think there's one thing, I'd be curious to hear your thoughts on this. Life is just, biology is a layer on top of geology, okay? and as such, what life does is...
Wait, just to be clear, we would later learn even that some significant fraction of Earth's biomass lives underground as a participant in the geology that's there. Yeah. So it's not just life on Earth and then hand over to the geologist. Right. There's this interwoven. There's this zone where the two have to make nice in the coffee lounge, right? Yep. Okay.
And so life's job in the universe is to accelerate our production of entropy and heat, abiding by, if you will, the second law of thermodynamics. And so when it comes to Titan and say weird life on Titan in a non-polar solvent, I think as long as there is some energy that needs to be dissipated in some way, perhaps biology will fill that energetic niche, even if it requires going way out of the box of what we're able to conceive of.
Have you ever wanted one of your questions on the universe answered? We all have questions about the universe. From black holes to quasars, quantum entanglement, wormholes. There is no end to the depths of cosmic curiosity. Well, the entry level of Patreon membership with StarTalk gets you just that. I think it starts at $5 a month. You have access to the question line that reaches our Cosmic Query programming. And not only that, we produce a special Cosmic Queries installment just for Patreon members.
If you weren't the director of the Hayden Planetarium, what do you think you would be doing?
Okay, but this had to be another universe. It wouldn't happen in this universe.
Okay.
I'd be a songwriter for Broadway musicals.
Ooh!
So that's the entry level, and the perks ascend from there. There's a level, in fact, where we send you an autographed copy of one of my latest books. Right now, it's Starry Messenger, Cosmic Perspectives on Civilization. And it's signed with my fancy fountain pen with purple ink. So I invite you to just check the link below. And all of that money goes to our ability to experiment with new ways of bringing the universe down to Earth. So thank you for those who have already joined. And we welcome others to participate in this grand adventure of what it is to bring the universe down to Earth. As always, keep looking up. I'm reminded in the movie 2010, where we learn where the life form that made the monolith came from 2001. And do you remember where it came from?
Remind me.
Is it Europa?
Well, but the
I don't know
actual,
where it came from, but that was the solar system's outpost of this life was Europa.
That's right.
And I think they found chlorophyll on the surface of Europa.
Right. So back then there was the thinking that, and in the movie they show the sort of a green underneath the ice, and that would require a very thin ice shell at Europa. Mm-hmm. So that's where the sort of monolith stuff originates, but then it goes back to some distant place in the galaxy. Yeah, and 2001, 2010, some of my favorite movies, but I get no ending of people saying attempt no landing on Europa based on that movie. But of course...
Are you sure? You don't have to... Are you authorized to divulge where we're not supposed to... Yeah, because...
In the books.
Wait, dude, you're on a mission called Europa Clipper. You're going to Europa. Yep. Low dipping over Europa, but you're not landing there.
That's right, but doing beautiful flybys.
But you're not landing there.
Correct.
You're heeding the warnings of the aliens in 2010.
No, not at all. There's a cadence.
Of course, that's what you'd have to say. It's just what you should say. But let's talk about Europa Clipper.
Yeah.
6-year mission. there. And
6 years to get there.
yeah. And then you hang out there a bit, orbiting Jupiter, but doing some close flybys of Europa.
That's right.
And it's very exciting.
Oh, it's tremendously exciting. And when we say flybys, normally when we think about a spacecraft flying by a world, it's thousands of kilometers away. The engineers here at JPL, the pinball wizards, are able to get the Clipper spacecraft.
But pinball wizards, because you have multiple.
The gravity of all
Europa Clipper is getting a gravity assist from what?
From Earth and Mars, and then once it's in the Jovian system.
Wait, so this is a 2-cushion pull shot to get to
to get to Jupiter.
To get to Jupiter.
But once it's at Jupiter, then we go off the cushions of Ganymede and Callisto a bit.
So you get more gravity assists from the moons.
That's right.
Very cool.
Well, by that time, it's gravity assists to slow us down.
Yeah, because people forget that you can gravity assist in either way for your energetics.
Yeah.
Yeah.
And so Ganymede and Callisto, it's a beautiful thing about the Jovian system, the Jupiter system, where those larger moons can actually help out the spacecraft engineers to get into all sorts of different orbits. And so we'll pinball around.
Hence pinball wizards.
Yeah, exactly.
Great title for them.
And,
wait, are they okay with the title?
I use this endearingly with my engineering colleagues all the time, and they like it.
They like it. Okay. Right.
And so we pinball around Jupiter, and then we start going into these roughly 14-day pedals orbiting Jupiter and making these close flybys of Europa.
Like petals of a flower.
Petals of a flower,
around.
exactly.
Yeah.
Or think about like those spirograph.
I've had
things.
one, spirograph.
And so we'll orbit Jupiter, but make these flybys of Europa, and the close approaches.
How close are you going to get?
25 kilometers, and some of the closest ones. And
that's as close as any object has ever swung by anything.
It's going to be extraordinary. And the images, 0.5 meter per pixel.
What?
Yeah. And the Galileo images. So think about how extraordinary the images from
Galileo,
the
the spacecraft.
Yeah.
Okay, because he was an
not
actual
the
person.
astronomer. He didn't have that
and he did have a telescope, and he
Right.
did look at Jupiter.
Yeah, so let's make sure we're on the right.
Galileo did not have
history.
0.5 meter per pixel resolution.
So Galileo, the astronomer,
Yes.
point of light.
Yeah.
Galileo, the spacecraft. We get beautiful pictures at kilometer scale.
Suppose you could just tell Galileo what you're about to do. What a privilege that would be.
Oh, absolutely. I mean, and that's 400 years ago, 400 plus years
That's
ago.
that's nothing.
That's nothing.
In the history of our species.
Yeah.
Just say, one day we're going to go there.
Yeah.
One of your Medicean moons.
Yep.
So you're going to close view of the surface ice.
Yeah.
But you're not looking at the water below, and that's what you really care about.
Right. And so what Clipper has on board are cameras to give us pictures of the surface, spectrometers to tell us about the surface composition. And by looking at the surface ice, we know from Galileo spacecraft, from telescopes, that
And Hubble helps out.
and Hubble, and that the ice of Europa serves as a window into the ocean below. So using the spectrometers and looking at the ice, we will get a bit of a fingerprint of the ocean chemistry.
But that's only because there are cracks that might fill in with the water
Geology,
and then refreeze.
That's right. Subduction, subsumption, overturn.
What is subsumption?
That
That shouldn't even be a word. Just my opinion here.
Yeah.
Subsumption?
Yeah, is a term coined by some colleagues of mine. Just
You all just made up the word. No,
as we do,
because
right?
I know there's subduction,
Right.
as when a continental plate goes under.
That's right.
And then there's
and so subsumption
give me some other words here.
is kind of thinking about how that might occur on an icy shell. So for the most part, you can think about subsumption as subduction, but on an icy world with perhaps some other things mixed in.
Did it really need another word? Okay, fine.
Debatable. But so with Clipper, we've got these cameras and spectrometers and then mass spectrometers that will allow us to taste any plume material coming out of Europa. Well, we can taste any organic compounds, carbon compounds.
So taste, you mean almost literally taste, because if you have the molecules and you have something to detect the molecule, you've basically tasted the molecule.
That's right, exactly. And so
With your machine.
I'm a co-investigator on the SUDA instrument, which is a dust analyzer mass spectrometer. Surface analyzer for dust at Europa.
Okay.
It's acronyms these days are
Okay.
all over the place.
I'll give you that.
Yeah.
I'll give you a hall pass on that one.
So they don't necessarily go by the first letter of the word anymore.
Okay, so that's more of a passive experiment because you're not aiming for those. It has to sort of come to you if it happens to be spewed forth from the surface.
Exactly. Think about a kid with a bucket running through a snowstorm. It's much more muted than that at Europa, but we will be getting those compounds into our bucket and passing them through the mass spectrometer.
And these aren't big plumes like you find on Enceladus, but there is certainly upward movement.
Yeah, so I've been on a team that's used the Hubble Space Telescope and the James Webb Space Telescope to look for plumes on Europa.
Isn't it great we have telescopes that can see the edge of the universe,
extraordinary.
and then right in front of our nose as well? This is we got good people.
We can get amazing things done when
we got
we
some
set our
people.
minds to it.
Our people are good folks. Not just the astronomers, but of course the engineers that actually make it happen.
Right.
Shout out to the engineers here. Okay,
they get the hard stuff done. So Enceladus is a tiny moon. It's only 500 kilometers in diameter and very low gravity. And so plumes on Enceladus go out for hundreds of kilometers. Europa is about the size of our moon, and Europa's gravity is about 1/7.
So Europa is way bigger.
Way bigger. 3,000 kilometers in diameter.
I didn't even think about that.
Yeah. And so
500 kilometers in American speak, that's like 300 miles across.
Like that, yeah.
All right. It's still a nice object, but
Yeah,
it's not like Europa.
Right. And
so what are the chances of you seeing sort of macroscopic life that might have bubbled up and landed on the surface, like fishes flopping?
Are you asking if our bucket's going to catch a squid?
And you reminded me, you advised on the movie, the sci-fi movie, low budget, but still carefully conceived and executed movie, The Europa Report.
That's correct, yep.
And I have a tiny cameo in
You
that.
do?
I did a tiny little cameo. I think it was on CNN. They used actual footage of me on actual news, commenting. I said, I want to go ice fishing on Europa, cut a hole, lower a submersible, and see what's there. And that was expressing my enthusiasm for this.
You and I, if we could fish on Europa.
Oh, man. So you were an advisor to that film.
That's right. Okay, and they did a fantastic job.
That's why it was so good. Not because I was in it, but because they thought about the science.
Well, one of the really cool things, I've done some consulting on various movies, and I was like, hey, team, if we're going to do Europa, we got to do Europa right. And so they didn't know that much about the radiation environment of Europa.
From Jupiter.
From Jupiter,
yes.
Exactly. And so that's factored into the movie and becomes sort of central to the story. And on Europa, that irradiation of the surface would kill an astronaut. But coming back to habitability, one of the things that we're looking for with Europa Clipper is how some of the radiation-driven chemistry on the surface of Europa could positively affect the chemistry of the ocean and the habitability of the ocean. Let me give you an example. Sulfur comes from volcanoes on Io. The eruptions on Io exude sulfur, and some of that sulfur actually lands on Europa.
This is sulfur that has been spewed forth from volcanoes faster than the escape velocity of Io.
That's right.
Thereby contributing to the general orbital environment of Jupiter.
That's right. It gets spun up in Jupiter's magnetic field. Next thing you know, that sulfur ion is slamming.
Well, it's an ion, so it responds to the very strong magnetic field.
That's right. But then, so some of that sulfur impacts Europa and then gets radiolytically processed into sulfate and other forms of sulfur, which then, if mixed into the ocean,
Sulfate.
Microbes on Earth
love
sulfate. And then get this. So what happens when you split apart H2O, water? You get OH and H. Some of that H escapes to space. Some of the OH recombines with another OH, forming H2O2. H2O2 is hydrogen peroxide. We have observed...
Which is the same thing as what anyone would call peroxide.
Exactly. At the pharmacy.
In the pharmacy, yes.
Yeah, and so...
That's that old joke. You know the old joke?
No, what's that?
Someone goes to the bar and said, "I'd like some H2O." And then they hand him a glass of water. And then someone sees that and says, "I want some H2O too."
And so they go get a glass of peroxide.
And then they drink it. That'd be a very chemically literate bartender.
Right. And not a very tasty drink. But so get this, that radiation processing of the ice, of the H2, of the water ice on Europa, leads to the formation of hydrogen peroxide, H2O2, which then that also gets radiolytically processed or decays to O2, oxygen. And telescopically, we see hydrogen peroxide and oxygen in the surface ice
You
of
have to be
Europa.
very clever to go from one step to the other to see this through. A game of dominoes, and you don't know where the dominoes are, but you think you do, and maybe it is. Yeah. And if it is, this leads to that, and then you have what you need.
Right. Except we actually observe it. So to be clear, we see condensed phase oxygen on the surface of Europa.
And you think that's how you get it.
Right. We get it radiolytically. I do that in my lab. And
I love when you say that. I do it in my lab. Need some of that? My lab.
And that's the fun of like lab and spacecraft.
I know, it's great. It's great. And they go hand in hand.
Right.
Yeah.
Yeah. And so we can make predictions and it's a lot of fun. But so, of course, we know that oxygen is very useful for life on Earth, not just for microbes, but for...
Well, for our kind of life.
For macrofauna.
Anaerobic life does not like oxygen,
that's
just
right.
to be clear.
And they love sulfur and methane, all sorts of other things. But so here you are, the radiation environment on the surface of Europa could produce compounds, which then, if delivered to the ocean through subduction, subsumption, whatever you want to use, could help provide rich chemistry to the ocean to sustain a biosphere within Europa's ocean.
And this will give you some of the chemical gradient you described that you
exactly.
need.
So you got hydrothermal vents on the bottom of the ocean spewing out things like methane and hydrogen and sulfide. And then from the ice shell, you might have things like oxygen and sulfate. So you can connect the battery, the biochemical battery.
And that's how you make Godzilla.
At least
this is the recipe for Godzilla.
Yeah.
So we got to wrap this up. Just one point. I care a lot about words and what they mean and how they're received. Europa has water underneath ice, yet you named this mission Europa Clipper. Mm-hmm. And a clipper ship from the 19th century floats on water.
Right.
Swiftly.
Yeah.
So who came up with the word clipper?
Because
that's a little... You're not floating anywhere.
Right,
You're still...
So they're in the early days, remember that during the gold rush, clipper ships were used to very quickly get people from New York City to San Francisco.
Yeah, they're some of the fastest ships made. They're narrower, a lot of sails. Yeah. The wind can take you. Before steamships, of course.
Right. Yeah.
Right.
And so...
By the way, I think the phrase, let's get there on a good clip, I think that comes from clipper ships.
A
clip is swiftly.
Yeah.
A clipper ship gets you there fast.
Yeah.
So I know you're getting there fast because you strip down the Falcon Heavy. The Falcon Heavy doesn't even have return stages because that uses weight that you could put in your payload. Right. So you strip it down, put it all in the payload, get it out there as fast as you can, get your two gravity assists. Yeah. You're there in 6 years.
That's right.
Yeah. So in that sense, it was a clipper, but not in the sense that it's floating anywhere. I got to get that off my chest.
100%. Yeah. And some of that clipper terminology goes back to variation in launch vehicles and stuff.
Okay. All right. Yeah. Well, Kevin, great to have you back.
Thanks so much, Neil. My pleasure. And great to see you. And it's an exciting time.
So if something bad or good happens to the Clipper mission, we got to get you back on to talk about it. Okay. When good
laugh will cry.
When all the good things happen, we got to get you back on. We won't do it while you're busily receiving the data, but if there's a break in there, you got to come back on.
Anytime.
And we can find your book, Alien Oceans.
Alien Oceans.
I love the assonance there, Alien Oceans.
The search for life in the depths of space.
Yes, there you go. All right, good luck with that.
Thanks so much.
For sure. This has been Star Talk, a JPL edition. Oh, yeah. Neil deGrasse Tyson bidding you, as always, as they do here, to keep looking up. This is Star Talk, Things You Thought You Knew edition. This is where we reveal the science underbelly of things that are just in our lives that maybe you never thought about. And I got with me my co-host, Chuck Nice, as always. Let's dig in. Chuck.
Yes.
I got a fast one for you.
Alrighty.
This one is going to be about wheels.
Okay. I'm going to say, I'll say a bit pedestrian for you. Just
Okay. Would it be any more pedestrian than water towers?
Ooh, good point. Only our
went viral.
Still the most popular one of these that we've done, I think.
Would have never thought that one would have landed the way it did.
Couple million people were just like, water towers, man. Gotta know about the water towers. This is amazing.
It's got like 5 million views.
I know, that's right. Oh my God, water towers.
So maybe the wheels will do the same thing. You ready?
Okay.
So, did you know that if you're driving down the road,
okay,
pick a speed, 60 miles an hour.
Nah, that ain't me.
Oh, okay, whatever. Sorry.
You got to bump that up by about 25 miles, and now we talking.
At whatever speed you're going,
okay,
there is a part of your car,
all right,
that is going forward at 0 miles per hour at all times.
All right, this already got interesting because I have no idea what you're talking about right now.
There's another part of your car that's going forward at twice that speed. At every moment.
Oh, God. Okay.
What?
Oh, Jesus.
Okay.
Oh.
All right.
Okay.
So, okay, you ready? Okay, are you seated?
Right.
Okay, here we go.
Okay, here we go.
Okay. It's all happening in your wheels. So, the part of the wheel at any moment
that's
in contact with the pavement is not moving at all.
That's right. Damn.
If your car were skidding,
right,
then the part of the wheel in contact with the road would be moving forward.
Would be moving forward.
At the rate you're skidding forward.
But that's why you're moving forward.
It's why you're moving forward.
It's why you're moving forward.
Because part of the wheel is not moving at all.
Exactly. Because if it were, you'd be spinning in place.
You'd be spinning in place. Correct.
By the way, okay. Now, you know what, man? You did it again. You did it again.
Stop.
Because I'm gonna let you know. I gotta say, first of all, this is what I'm gonna do right now. I'm gonna publicly apologize to you for all that shit I was thinking. Because I was let me tell you something. I was thinking some stuff. I'm going to apologize to you right now because you were like, all right, Chuck, we're going to talk about wheels. I'm like, this brother done lost his damn mind. We're going to talk about wheels. Seriously? But you did it. Go ahead. Let's go for it.
Let's keep going. Going. So the center of the wheel,
right,
which is... okay, it's spinning, but the exact center is going forward at the same speed the car is.
Absolutely.
Okay? The top of the wheel is going forward at twice the speed of the car.
Twice the speed of the car.
Okay?
Just like
at twice the speed.
Right. Wow.
Okay, because notice, if the chassis of the car is moving at the speed of the car, obviously, the top of the wheel is moving faster than the chassis.
Right.
Okay? It's moving past the chassis. The top of the wheel well. The top of the wheel well is going forward at your speed, at your speedometer speed. The top of the wheel is going faster than that to come around to the bottom so that it's not moving at all.
That's incredible.
And if you run the math on that, you get 0 at the bottom, the speed of the car in the middle of the wheel, and twice the speed of the car at the top of the wheel. And so this is the geometry, the math, and the physics of an axled wheel on any moving vehicle? What are you doing? Chuck is Chuck is smoking something.
I'm just saying. I'm ready to talk about this all day.
Chuck is smoking. Okay, but wait, there's more.
That's awesome. That is awesome.
But wait,
and
there's more.
because I'm
So you know
picturing
what
a dot on the wheel and a dot at the chassis, and then it comes up. It has to go faster than the top.
Faster.
Has to go faster, so it could come
than the top of the wheel well.
That's right.
So that it can come around. Correct. So now think of the wheel that's on a train. Okay. The train wheels are different, all right? They're different from car wheels, obviously. So there's the metal flat part that touches the metal rails. But then there's another part that's like an outer, where should I use that? It's like a coupler. There's an outer part that extends outside of the track.
Right.
Okay? Can you picture this? It's not like just rolling on a track. It's like a lip.
Like a lip on the wheel itself.
A lip that extends outside of the track, which enables the train to stay on the track. Otherwise, we'll just drive off, right? So these lips that are exterior to the wheels keep the train aligned on the track, okay?
Right.
But here's what's interesting. They dip below the contact point of the wheel and the rail.
Correct.
That by a little bit, by whatever it is, they dip below.
Right.
All right. Well, if the top of your wheel is going twice the speed, the center of the wheel is going the speed, the bottom of the wheel is going 0, anything lower than the bottom of the wheel is moving backwards.
Oh, snap. That's right.
Okay. Okay.
It's going in reverse.
It's going reverse. For any train, there are parts of that train that are moving backwards on the track at all times.
Wow. That's pretty wild.
And just picture that. You know, there's the wheel rolling. Right. The part that's below the contact point is moving backward. It actually lands in a place behind where it started.
Right.
That means it moved backwards.
That's right. That's insane.
I just thought I'd put that out there. I know it's nothing deeper than that. It's
the next time I tie up a woman and put her on the tracks, I'm gonna let her know that you're gonna learn something.
Is this what you do, Chuck? Okay.
As I twirl my mustache.
Now, here's something interesting. Are you ready?
Go for it.
So that means there's a part of your car that's going at all speeds from 0 up to twice the speed of the car, correct?
That's right.
Okay. So imagine this. Imagine attaching some device to your wheel that sends out a microwave signal, and you can adjust it up or down, okay? From the center of the wheel to the outer rim, and sends out, or from the center of the wheel to the bottom, sends out a microwave signal that will report a speed of your car at any speed you choose. So the police officer's there with the radar gun, with the return signal that's going 30 miles an hour, even though you're going 60.
Mm-hmm.
Yes, so they'll get the reflected signal off of your car, right? But if you can override that with a more powerful signal sent from your wheels, you can broadcast any speed you choose down to 0 if it's attached to the wheel.
Right, which is that's the speed I'm choosing, by the way.
Well, you can't do 0 because they know you're lying.
Well,
but
that's
any place between the center of the wheel and the bottom
of the wheel.
You can broadcast a speed of that spinning wheel at any speed less than your actual driving speed.
Wow.
But to configure this would be really weird, and how to make that happen, because it has to be moving with the tire. I don't know how you would design the engineering of that, but it's just something to think about. Because there's always a part of your car that's going everywhere from the speed of your car down to 0 and up to twice the speed of the car.
Well, maybe, when the cop pulls you over, you can just tell him, I don't know what speed you recorded, but I don't know. You should have been looking at the bottom of my wheels.
Where was it? Yeah, that'll work in court. So that's all I have to say about wheels.
That was pretty damn good. I mean, sorry, pardon my language. That was pretty doggone good. I'm completely surprised, taken aback by this one.
Yeah, and there's another kind of wheel, which is the shape of the object that rotates within a Wankel engine. So if you imagine an equilateral triangle, but curve the corners of it and make the sides a little bit convex, right? So it's a triangle.
I had a Mazda once.
Oh, you did? Was it with a Wankel engine?
Yeah,
okay.
I had a Mazda.
So that shape, interestingly, the distance from the bottom to the top remains the same no matter how it's oriented. Right. So if you roll it along I made one of these shapes. In fact, I don't have one with me here. We might have to do another explainer.
We used to call them spirographs when I was a kid.
Okay, yeah. They're related. They're related,
yes,
right?
Yeah.
They're related geometry to it. So if you take a plank and place it on top of one of these triangular shapes and roll it, the plank will be absolutely steady. Even though it looks like the thing is bobbing up and down. It's because there's no central axle to it.
Right.
Okay, we think a wheel that gives you a smooth ride needs one central axle because a wheel is the same distance to each point on the rim. You can design a shape where the top is always the same distance from the bottom, even though the center is moving in your spirographian sort of way.
Nice.
So I actually built one of these when I was a kid in woodshop in 7th grade, and I don't think it's with me here.
That is
in a closet somewhere. I'm gonna have to dig it up, and we'll do another one. Just fun things to do with a Wankel engine.
Nice. Yeah, it's an unfortunate name, but yeah.
I know, right? It's a little weird. It is a little weird, but it's one of the many engines that have been developed over the years to convert chemical energy into kinetic energy. And so maybe we'll do it. I know. We'll do an explainer just on engines and the history of engines.
Oh, that's a great one.
Why they differ from each other and where they're headed. That's a good one.
That is a good one.
And now you know that part of your car ain't moving at all.
But don't use that as the excuse when you get pulled over. That's it.
Or don't experiment with how the cop will react if you give that as an excuse.
Right.
You don't want to experiment. We've got to take a quick break, but when we come back, the second segment of Things You Thought You Knew on startalk. We're back. startalk, Things You Thought You Knew edition. Still here with my co-host, Chuck Nice. Let's dig right in. Chuck, another explainer.
Okay.
Is bubbling up within me. Okay.
Right. Now, you sure that that's an explainer?
Or I gotta go to the bathroom. Is that what you're saying?
I was going to say, what'd you have for lunch? Because,
So I was just thinking how much we take for granted about when we use the word energy. And it has profound origins. I mean, our understanding of energy has profound origins. The brilliance of Isaac Newton, who, discovered the laws of optics and gravity and motion and invented calculus.
Mm-hmm.
Energy was not a fully developed concept in his time.
Right.
And so I just want to sort of spend a few minutes offering an appreciation for a triumph of the human intellect to figure out what the hell energy is and then how to manufacture it and exploit it. I just want to spend a few minutes. This is like a public service announcement for energy out there. Energy is not a thing, right? You can say a rock is a thing and you can point to it, or planet is a thing. And energy is not a thing. So it was delayed in our ability to understand what it was and how to think about it. So we knew some things. For example, when you had a cannon, back when cannons were like a popular tool in warfare,
right?
There were physicists at the time who said, I have a cannonball and have this gunpowder. and the cannon is made of iron, then I fire it. And if I keep doing this, the cannon gets hotter and hotter. Well, where's that heat coming from? So what is it? And so in the urge to turn energy into a thing, early ideas was that there was energy was a fluid, was a thing that could move in and out of objects. Okay. One of them, they called it phlogiston. Another one was a caloric. These were words invented to try to think about energy as a thing, and then it moves, right, and it's got to be somewhere. And so a hot cannon had more of this in it than a cold cannon. Gotcha. And so that was, you had to start somewhere. We were crawling before we even could walk. And it wasn't until we understood molecules and atoms and that we were able to say, okay, and what role friction plays in this. We were able to say, so you can store energy in different ways. And when you store it, it's not manifesting itself. It's not saying, here I am, look, it's not really doing that. And when you're storing it, no, the object is not in motion. No, the object is not, is not all these things that it is when it's manifesting. So let's take the simplest case, a roller coaster, okay?
Right.
Every roller coaster, the first ascent is the highest.
Yeah.
Okay? So what's going on? So there you go, and you're leaning back, and this thing cranks you up. It is endowing you with energy, potential energy, stored energy, potential gravitational energy. When you get to the top, you can calculate how, because we have formulas for this, calculate how much gravitational energy it handed you. So I don't feel this energy. I don't know what you're talking about until I push you over that ledge.
Right.
Over the other side of that hill. Then what happens is your potential energy starts converting to mechanical energy, to kinetic energy. And it's an exact trade-off. An exact trade-off. So all that energy they gave you at the top,
right,
okay, now is returned with you speeding up as you descend.
And that is when
and you had
the
so much
ham
energy
sandwich becomes actual vomit.
Okay. That's a transformation of another kind, right? So, and it's this trade-off, and it goes back and forth as you go up hills and down. If you go up a shorter hill than the first one, okay, you have enough energy to reach the top of that hill because you started out with way more energy than that at an even higher hill.
Right.
You're going to lose some energy to friction. Okay. So in other words, you can't ascend back to a hill exactly the same height that you started in. Okay. Some energy will go to friction. And when you lose energy to friction, that makes heat. Okay. That's the source of heat when you lose energy. All right. So that's why the engine of your car gets hot.
Right.
Okay. Not all the energy that you started with got transferred to the motion of the car. The losses went to friction. The friction heated your engine gets hot. Okay. So in a roller coaster, you're converting gravitational potential energy to kinetic energy and back and forth and back and forth and back and forth. And if they designed it right, the frictional energy that you lose, okay, you don't go up higher and higher. The hills you go over have to get lower and lower. And there's the last one, then you come in for the stop.
Right.
So they gave you the energy when you started at the top of that hill. So that's gravitational potential energy becoming kinetic energy. That's what's going on there. And like I said, if you go back up a shorter hill, you'll slow down. Because some of that kinetic energy is giving back to you, so you can have another little lump of potential energy to take the next hill that comes after that. All right, so that's easy. We've had roller coasters forever. You can have imagined them forever ago. But it's more complicated, or a little more physics involved, if you want to say, this molecule has energy.
Right.
A molecule. Well, how am I going to get the energy out of the molecule? You're just sitting there. Oh, well, you can, in one case, burn it. Burn the molecule. Okay? Why is it that you can throw a log in the fire and the log is room temperature? You put in the fire, then the fire ignites the log and the log keeps burning. Mm-hmm. There's chemical potential energy in the molecules of the log. Where did that energy come from? Where did the log get that energy, Chuck? You tell me right now.
The log, it's from its molecules. It was storing.
Where did its molecules get their energy?
Oh, okay. Let me think about this. From their atoms.
What did the log used to be?
No, it used to be a tree.
A tree. How does a tree get energy?
From the sun.
Thank you. So, the sun builds molecules that contain stored energy. So that's why wood burns, because it has stored chemical energy given to it by the sun.
Look at that.
And it's just sitting there minding its own business.
Right.
But that's why fires in homes are so deadly, because there's all this potential energy stored in the molecules of organic matter, wood, if your house is made of wood,
right?
So that the whole thing burns, converting the chemical energy into thermal energy.
Wow.
So much of our lives is the conversion of energy of one form into another. And what happens while that's going on? So other forms of energy, there's energy in the nucleus of an atom.
Yes.
You split the nucleus and take it out. We make bombs doing that. Okay. So we turn nuclear energy into the kinetic energy of an explosion to do damage to things in warfare.
Gosh.
Okay. That's nuclear or chemical energy. Some chemicals will give you their energy not slowly, like a slowly burning log.
Right.
They'll give it to you catastrophically. All right. And we call those bombs. Okay.
Yep.
Or a firecracker. Catastrophically. Boom. The energy goes to break apart the firecracker, goes into the sound that it makes, the shock wave, all of that. So our lives and everything we do is nothing but a ballet of the conversion of energy from one form into another. So, but think about it. So you eat food that you look at the calorie content. That's how much energy it has. Okay. So then you consume it. You need energy to live, to move, your heart beats. All this requires energy. You're getting it from the calories of the food you eat. So what happens if you consume more calories than you need?
Got to store
Your
that.
body says, store that.
Store that energy.
So it creates chemical potential energy in the form of fat. And it stores it away.
I'm not fat. I'm just filled with potential. What you talking about? You see this? This is potential. I am potentially Michael B. Jordan. I am potentially Michael B. Jordan. That's what the potential.
My six-pack is just beneath the potential.
It's just beneath all this potential. You don't even know what you can have. I don't even know what you can have.
So,
no one knows what you can have because it's all potential.
And by the way, that conversion of your body's calories to your energy is not perfectly efficient. So what happens to that excess energy that's not converted? That's the inefficiency of your body. We're an engine of sorts. It's inefficient. So that inefficiency gets converted to heat. Mm-hmm. So your body heats up when you exercise.
Right.
It's a consequence of the inefficiency of your body. But your body loves that because now it's part of your temperature regulating system. But I'm just saying, when you exercise, your body heats up. In the same way you drive a car, the car heats up. Right. In the same way, the wheels and the tracks of a roller coaster are actually getting hot because of the inefficiencies of the conversion, because there's inefficiencies in every conversion of energy from one form to another. So the only point of this explainer is just to say, so much of what we do and how we live involves the clever conversion of energy from one form to another. Nuclear energy, molecular, chemical energy, which is molecular. We have kinetic energy, gravitational energy. All of this comes together, and our ability to exploit that in the service of civilization is one of the great triumphs of physics, especially 19th century physics.
Look at that.
Where they figured out, oh my gosh, look what we can do. Another quick one, just look at a locomotive, right? Well, what's going on there? Well, the locomotive, all right, I don't know if you remember, they'd have to fill up from water tanks every now and then. Okay, well, what does the water do? Well, a locomotive burns either coal or wood, and it heats so that's the chemical energy. It heats a vat of water, so it's got the stored chemical energy of the wood into the active thermal energy of the vibrating water molecules. They then evaporate, creating pressure for the steam to then move wheels to have the locomotive go forward.
Nice.
Oh my gosh. And that all started with solar energy that made the wood or the coal, that made the fire, that made the boiling water, that made the pressure that moved the wheels. All of this is a triumph of our understanding of energy.
Now, what you just said there, I can hear Exxon going, listen, guys, we're actually solar energy. Okay, so I just see it coming now.
Ultimately,
guys,
it started as solar energy.
This is solar energy, okay?
Fossil fuels started as solar energy. This is true.
Damn.
This is true. It reminds me, and we got to end right now. It reminds me of this bumper sticker that says "No nukes," right?
Right.
From the anti-nuke movement, and then the O in the "no" is an image of the sun.
Well,
it says "No nukes."
No nukes. Okay, yeah, exactly.
Okay. All right, I know what they mean.
Right.
They want you to do solar energy, but the sun makes its energy with nukes.
Right.
All right, just like make that clear.
Yeah.
Here, that's how it started that way. So anyhow, I just thought I'd put all that out there.
That's cool.
And so just to enhance our appreciation for what energy does for us and how being clever has enabled us to build civilization on the exploitation of converting energy from one form into another.
Yeah, it has built civilization, and ultimately it will destroy civilization.
Destroy it. On that happy note, Chuck, thank you. We got to take a quick break, but when we return, the third and final segment of Star Talks, Things You Thought You Knew. We're back. Star Talk, Things You Thought You Knew edition. In this segment, Chuck and I continue to explore the science that lives in the underbelly of things you always thought you knew. Chuck, what do you know about Medusa?
I don't want to see her. I know that. if she ever said to me, look here, I'm like, no.
Not looking.
No, I'm not looking. What you mean, look here?
Yeah, she makes eye contact with you, you turn to stone.
Right.
And she's famously in the night sky. She's immortalized.
Did not know that.
The severed head of Medusa is immortalized, held by the Perseus. Perseus is a constellation in the sky. And there's a star called Algol, which is a variable star. It changes its brightness over relatively short periods of time. That's why we call them variable stars. And the eye of the severed head is Algol. So this is Medusa, like, looking at you. It's pretty fun. And of course, Perseus was the hero in the story with Andromeda, who is the daughter of Cassiopeia. And she was, I don't remember why. Oh, Cassiopeia said she was more beautiful than the sea nymphs. And then out of punishment, they took her daughter and strapped her to the cliffs for the sea monster to come devour her.
Kraken.
And Perseus, the Kraken, right. And so the Perseus comes to save her, but he can't get there on foot. So out of the sea foam rises up Pegasus. And he flies on the back of Pegasus. Oh, he has to slay Medusa, all right?
Right.
And so he does it by looking at her, but through the reflection of his shield.
Right.
Okay? And that way it's not a direct direct sight line.
I can't believe she fell for that.
And fell, and backs up to her and slays her backwards. Right, that was pretty cool. And it cuts off her head and puts it in a sack. Perseus is in the sky, rides on the back to go save Andromeda by showing the severed head of Medusa to the Kraken, and the Kraken turns to stone and then crumbles away because he's too big to be stone, right?
I gotta say, that's a big chance that Perseus took, that, you know, the severed head would still be able to do its thing.
Good, yeah, rather than just with closed eyelids, right? You have to like pry open the eyelids with toothpicks or something to make that.
Exactly, because, you know, a lot of times, you know, he had to make sure she died with her eyes open, probably from the surprise of falling for that stupid trick of looking at her through a shield. So she died with her eyes like, I can't believe that I fell for this. Like,
is that what she sounds like?
That's Medusa. Oh my God, I can't believe I fell for this stupid trick.
Okay, so all of them are in the night sky. We got Andromeda, Medusa, Cassiopeia. The reason why I'm saying all this is there's a whole set of legends that derive from the expectation that when you look at someone or anything, that you're sending out some beam of energy or information or light, as though seeing was an active aspect of what it is to obtain information.
Right.
So I see you because I'm going out there and I'm getting you and bringing you back into my head. Right. So that is not how seeing works. And this was not established until about 1,300 years ago in the Middle East, in what we call the Golden Age of Islam. Al-Hazen, occasionally referred to as Al-Haytham, both of those I think are legitimate names for him, one of the great scientists of the era, an early scientist in the history of scientists, kept good notes, had hypotheses of how things worked. He looked at a cow eyeball, saw a lens, saw that you can make an image on the back of the eyeball, and he deduced that the act of sight is 100% passive.
All reception.
So you can't just give someone the Google eyes and have them say, oh, I feel someone's looking at me. People will still say that. But all experiments show that no, you cannot tell if you do it in a controlled setting. You cannot tell when someone's looking at you. Okay?
Unless you're in the subway. Because sometimes you're in the subway and you just get that feeling that comes up the back of your neck. And you turn, and there is some creepy person staring at you, and they don't turn away. They will not. That's how you know you're in New York. Any other place, you look at somebody, and they look away like, "Oh shoot, I was staring."
They look sheepish about having been caught.
I can't believe I was staring. You in New York, you turn at them, and they're just like, "That's right, I'm going to kill you." Like it's.
Don't scare people from the New York City subways. That's not what. Here's my point. Anytime you turn around because you think someone's staring at you and they are staring at you, you have not recorded the thousands of times people were also staring at you and you didn't turn around to notice. Okay? So this is when you do the control setting, this is the case. So it's just an interesting fact. The Bible stories about, who was it that turned back and she became a pillar of salt?
Lot's wife.
Is it because she observed or because because Sodom and Gomorrah, the light from Sodom and Gomorrah reached her eyes? Which was it?
Well,
or am I mixing my Bible stories here?
No, that was correct. It was actually both of that, both those things. She observed the destruction of Sodom and Gomorrah, and they were told, whatever you do, do not look back. And so she violated the directive, looked back at the destruction, and turned to stone in doing so.
Okay, so that case, that might not be her sending out a signal from her eyeballs. So that sounds like a more legit consequence of this, relative to Medusa looking at you, her eyes light up, and then you turn to stone. So it's an interesting history how you can, there can be mythologies that rise up around physiological misconceptions that make for interesting stories. right?
Right.
And people used to be thought of as dying of a broken heart, all right? Maybe it was an actual heart attack, all right? But, and, you know,
It was bacon. It was bacon.
Francis Bacon? Or
No,
bacon?
it was just bacon.
The bacon they...
That's just like he died of a broken heart. No, that's
You
called
ate too much bacon.
cholesterol. That's called cholesterol. The man had bacon with every single meal. And you know you can't do it.
But you don't want to take away the romance of dying of a broken heart. That's all.
No.
So it's just fun. So I don't object to misconceptions if you have no better explanation at the time, and it becomes part of sort of our cultural sense of the world. I mean, this is the richness and the depth of history that we experience as a culture. Who knows what they'll be saying about?
You know, here's the problem with that though. See,
What?
Someone of your particular acuity can say that. Can say this is part of the wondrous romance of life,
charming elements of our past.
charming elements of life that we're able, because you're a person who understands the scientific method. You're somebody who, believes in data and empiricism. You know, both. Okay, but the problem with that charming, that wonder, that these idiosyncratic, things that happen. That we attribute meaning to them, that we're attributing that meaning. We are affixing meaning to those things. They don't really have meaning. The problem is there are a bunch of dumbasses who actually believe.
Okay.
They believe this. It's no longer.
There's no excuse. Once we've learned how all this works, there's no excuse to continue to think it's true. And that's what you're talking about. The people who are delayed in their acceptance of objective realities. And I'm with you there. But I'm not going to judge people from long ago on today's standards.
Oh, okay. All right.
I'm going to say...
Okay. No, yep, you got me. Yeah, that's I got to give it to you
Okay.
there. They're
That's
perfectly acceptable. They had no other information, so therefore, boom, I get it.
Good, exactly. Exactly. And, right on down to those who imagined that someone having an epileptic seizure were being invaded by the devil.
Right.
Right. And so you go get the priest and they do the holy water.
Right.
And
then
they
seizure's
come out
over.
of these symptoms.
Right.
The seizure's over. The 20-minute seizure ends. It just ended because how far away is the church? 500 years ago. It's like 2 blocks away, right?
Exactly.
Just in time for the priest to get there. So we're trying to make sense of the world. And I don't, I'm okay
so funny
with that.
you use that as an example, because I think it's a great example, because we can actually see the brain now. We can see the activity of the brain and exactly what is happening in the brain that causes this epileptic fit. So we're not seeing the devil. What we're seeing is a neurosynaptic breakdown or malfunction.
Right.
And so, but where did the devil go? If you want to still believe that.
Right, but fine, in the face of science, just don't lead any science agencies that allocate research funding. Play a job for you if it's in a society. All right, Chuck, we got to end it there.
All right.
This has been yet another Star Talk explainer on some random subject you never thought you might be interested in, and maybe you're still not. I don't know. Who am I to tell? Well, we're out of time. That's a wrap on Star Talk's Things You Thought You Knew edition. Chuck, always good to have you. I'm Neil deGrasse Tyson, your personal astrophysicist. As always, I bid you to keep looking up.